So let's start. Thank you very much for all of you and for our jury, and also all of the people that will be among us with the dissertation, master dissertation of Felipe Camargo. I'd like to welcome Pierre MARUZEWSKY, a good friend of our university historically, and from EDF Hydro in Lyon. Thank you very much, Pierre, to be among us. And the second person is Taygoara Oliveira of our lab here in the University of Brasilia. Thank you very much to be among us also, and everybody to be here during this hour of presentation. It's a good thing to enlarge our relationship with the international collaboration with different partners in France, in the United States, and so on. It's the second thesis and dissertation that we did that during this time. We had did that during this time, and I will be happy to hear Felipe to start the presentation, and so we can do that. Thank you very much. I don't know if Rafael, no, Edgar is not here anymore. No. Okay.
Edgar is not here, Professor.
Yeah. Okay. Let's go. I will send you a WhatsApp message during the presentation. So, up to you, Felipe.
Okay. Thank you, Professor. I will share my presentation here with you. Okay. Everyone is seeing the presentation screen?
Yes, you may proceed.
Okay, thank you. So I will start. This presentation is, I made to at least 40 minutes, but I hope I can do in less time. And I will start now. Okay. Good morning, professors, and all the attendants here today. My name is Felipe Camargo, and I'm a master candidate from the postgraduate program of Mechanical Science from Brazilian University at the Environmental and Energy Lab. First, I appreciate Professor Taygoara and Dr. Pierre for accepting and being here today to evaluate and judge my work. I hope that I can perform a clear and brief presentation of my last 2 years' work. The title of my work is Image-Based Field Methodology to Determine Hydrokinetic Energy Potential, and was guided by Professor Brasil. So let's begin. This work is divided in 4 parts. First, the introduction, then my methodologies, then my field measurement and results, finish the conclusion, and then proceeding to any questions or doubts about the work. Energy is correlated to the life quality of human beings and all contemporary societies. Underdeveloped countries are and will continue to increase the electricity generation and consumption. There is a global demand to migrate the electricity mix to a net zero mix. Net zero means a huge decline in the use of coal, oil, and gas, traditional fossil fuel electricity generation. It's estimated that 51 billion tons of CO2 is emitted per year, and electricity generation counts of about 27% of this total amount. That gives approximately 13.7 billion tons of CO2. As we can see in this graph, Brazil is following the global tendency to invest in renewable energy, even if it's still in a shy way. It's estimated that an investment of $4 trillion per year will have to occur to achieve net zero until 2050. This is a huge opportunity to Brazil generate jobs and return to the growth of development. Brazil has a particular grid compared to the world. The Brazilian electricity mix is predominantly renewable, with most of the generation coming from hydropower. The Brazilian power sector is divided into two large systems, the interlinked one and the isolated one. The isolated system includes small local grids, mainly in the northeast Amazon. The energy supply of these off-grid systems is based on diesel generators, so they emit much more green gases than a citizen connect 24 hours a day to the conventional grid. There are 237 locations in Brazil that does not have access to electricity grid. That is about 2 million Brazilians. So, motivated by this global demand to expand the supply of clean and renewable energy and to expand the electricity generation option to isolate communities in conjunction with knowing that Brazil will need more energy to improve the development of the country, this work will apply and review a technique to determine the hydrokinetic potential from rivers. This technique is called LSPAV, an experimental technique derived originally from the standard particulate image velocimeter method, the PIV. The PIV method consists in using a camera and a speckle laser to map the line at a constant velocity along a stream. Knowing the time between each trigger pulse and the camera angle concerning the illuminated flux is possible to determine the velocity of the field. So a good definition of PIV is given by MUST. It's a precise quantitative measurement of velocity vectors of a fluid in a very large number of points simultaneously. Then, with the advance of technology, scientists start to apply this method in large-scale measurements. The first test was carried out in Japanese rivers, and from there it serves the name LSPAV. Several river velocity measurements have been carried out around the world since then. Japan, France, United States, United Kingdom, Paraguay, Argentina, and Brazil. The basic setup to perform LSPAV measurements is flow visualization, illumination, image recording, and image processing. To compare the superficial velocity measured by the LSPAV technique, an ADCP equipment was used. The acoustic Doppler current profile is a multi-band vertical acoustic beam sensor that transmits sound pulse at a fixed frequency in the column of water and listen to the return echo from small suspended particles moving in the acoustic beam. The accuracy of the estimated velocity is relatively good compared to alternative conventional measurement procedures. The LSPAV and the ADCP measures velocities will be used to estimate the hydrokinetic potential from three different locations. Hydrokinetic energy is defined as the energy associated with the movement of water, and the power density associated with the kinetic energy of the water flow can be quantified by this equation: 1/2 of the density of the liquid times the velocity power to the third. So, the main objective of this work is to study and review the LSPAV method to perform measurements and define the superficial velocity from rivers and channels. The secondary objectives are: compare the hydrokinetic potential calculated with the velocity measurements from the LSPAV and the ADCP techniques, perform measurements in different conditions from rivers and channels, analyze if the addition of a natural tracers improves the LSPAV technique. Also, a detailed explanation of the LSPAV methodology is presented, trust it can be replicated. Now, the methodology part starts. As previously talked about, two field methodologies were applied for this work. The LSPAV method, using a camera and a drone, and the ADCP measurements using the M9 equipment. First, the LSPAV technique will be explained, how data was collected and how it was handled. Then, the ADCP equipment. Also, a simplified explanation of how hydrokinetic potential works will be presented, and how both methodologies related to it. The LSPAV technique has four main components: flow visualization, illumination, image recording, and image processing. Basically, with any camera recording the flow of a river, it's possible to make an LSPAV analysis. The sequence to apply this method is define a region of interest in the river or channel and record the flow. Then, process the video with two graphical users interface, the GUI softwares. And finally, plot the results with Python libraries. The camera used for recording the flow is from a drone, from DJI company, the Mavic Air 2. There's a quick video here. Okay. So, define and inspect the site location is a very important test to perform at any river characterization. Flow visualization for the LSPV procedure is crucial because it's necessary to know if it's possible to record the flow of the river with the camera, and there's not too much vegetation around that can prejudice the footage. At all sites that we perform measurements, an overfly of the drone is performed to the site where the analysis would occur. The record of the flow was made with the drone positioned stationary above the river and must be flying at a specific altitude above the water so the wind created from the helices drones do not affect the river motions. To improve flow visualization, it's common to add some type of natural tracer to the river. This natural tracer is added upstream to the region of interest, where the analysis will occur. In our experiment conduct, the tracer was sawdust, which is a biodegradable tracer that will cause no harm to the environment siting. So, after deciding the site location, the recording device, paying special attention to the natural conditions around the flow and to the illumination that is presented at the site, an important step to guarantee a good execution of the technique is necessary to mention: the ground control points. These 4 spots at this image that look like a chessboard. It's indispensable to know a physical measurement from the field that appears in the record to be possible to calibrate the analysis to obtain the velocity in a traditional measurement system, like meters per second. After registering the image of the desired river, the image processing phase starts using 2 GIFs. The softwares that we use are River and PVLab. And following this simplified flowchart, the image processing phase will be explained. The first step is to input the video record into the River program. A toolbox with the option to extract the frames will be presented. The duration of the film is shown and also the ratio that was recorded. The time between frames is given, and it's important to register this value. Velocity is displacement over time, so knowing how much time passed between each frame is a piece of crucial information to calculate the superficial velocity of this method. The toolbox gives the option to extract the frames in grayscale and to perform a correction in lens distortion. Both options are marked because in the following step of the processing phase, having the frames in grayscale and a lens distortion correction improves the quality of the processing. This works use a non-fixed camera to register the river flow. Although the lens correction fixed distortion that occurs, there's another problem with the image collected by a non-fixed camera. The drone that is flying above the river is in stationary flight and can still change its fixed position due to wind or from its own flying mode. So, an additional step is performed to guarantee that the frames that are being analyzed are from the same position. The River program has the option to unshake the video's recording, dry a mask where it's designed to implement the LSPV. After the extraction is complete, it's obtained 600 frames in grayscale with the distortion from the camera fixed. Importing all the frames to the PVLab program is chosen the option to compare each frame in sequence instead of parallel frame in sequence. So the first frame will be analyzed with the second one, then the second one with the third one, and so on. With all the frames imported, the next step is to decide the region of interest. That is the region where the velocity vector field will be calculated. The program often offers the option to draw a mask in the region of interest to not perform a velocity analysis in this part. In this image, it's possible to see the blue dashed line that defines the region of interest, and the red mask that defines where not to perform a velocity analysis. Previously, when the importance of performance, the lens correction, and the unshake options in the river program was mentioned, it was just for when it came the time to define the region of interest and the mask. All frames were with the same region of interest and the same mask positioned in the same place. Here we have an example for analysis where the lens correction and the unshake of the image was not executed. We can clearly see how much it dislocates from the first frame to the last one. Moving on with the processing phase, with all the frames imported and with the region of interest in the mask established, there is a multiple filter disposal at PVLab to improve the image analysis. The enhancement of images before the actual image correlation takes place improve the quality of the measurements. The pre-processing techniques that are accessible in PVLabs are Clare filter, high pass filter, and capping filter. With all the filters applied to the frames, it's necessary to set the interrogation areas in the defined region of interest. Interrogation areas are small sub-images where a pair of frames are cross-correlated to derive the most probable particle displacement in the interrogation area. In essence, cross-correlation is a statistical pattern match technique that tries to find a particular pattern from interrogation area A in interrogation area B. This statistical technique is implemented with the discrete cross-correlation function. The idea here is to characterize the pixel inside this box, calling the characterized pixel of interrogation point, and search for the same pattern in the next frame of the image pair. This search is made by solving the cross-correlation equation. And there are two common approaches to solve this equation. The most straightforward approach is to compute the correlation matrix in the spatial domain. This approach is called direct cross-correlation. The other approach is to compute the correlation matrix in the frequency domain, and is called discrete Fourier transformation. Both options are available at PVLab, and both have their advantages and disadvantages. The discrete Fourier transformation option was chosen to perform this work. So, with all the frames evaluated and the displays between frames calculated, the final part of the LSPAV analysis is to calibrate the frames with a measure from the side location. Using the ground control points, the calibration occurs using a point-click option to set the size of it. Also, it's required to add the time between frame that was obtained in the frame extraction at the river program. So, after all these steps, the velocity vector field is estimated. An example can be seen here in this video from the Rodeador River. The green vectors indicate the direction of the flow, and as was mentioned, the mask it was not performed, in this red mask, was not performed any velocity analysis. The idea is to analyze velocity in different cross-sections from the defined region of interest, so it's possible to compare with measures made by the ADCP equipment. It was chosen to perform 3 extractions to analyze. The first extraction at the bottom of the region of interest, then in the middle, and finally on the top, always in the direction of the river flow. With all the files extracted, a script in Python language was writing to read and generate graphics. So here we have our first graph. There's 600 box plots plot together from one edge to another of the river. In the green line here is a mean value for each velocity calculated. And these black dots here are outliers. Then, only the mean velocity from each section, comparing the methods with sawdust and without sawdust. The blue line are without sawdust, and the green line is with sawdust. And now we proceed to the ADCP measurements. The ADCP equipment using the field measurements was the River Survive M9 from Suntech company. The M9 equipment is a robust and highly accurate system specifically designed to measure river discharges, 3-dimensional water currents, depths, and bathymetries from a moving or stationary vessel. The goal is to be able to measure velocity that are representative to the mean channel velocities. ADCP transmits sound pulses at a fixed frequency in the column of water and listen to the return echoes from small suspended particles moving the acoustic beam. To measure velocity, the focus is on the change in frequency of the acoustic sound. Because acoustic ping is a wave, it obeys the Snell law. So it's possible to calculate the change in the speed and the direction of a wave when it travels from a meter of one density into a meter of another. The change in frequency is calculated from each layer by those equations. So finally, rearrange these equations with the Snell law is possible to calculate the velocity. Measuring accurate water velocities anywhere in the water column is purely a function of the frequency of the transducers F, the angle of the transducers theta, and the speed of sound c. The M9 equipment is a robust and highly accurate acoustic Doppler current profile system. The equipment works integrated with a RTK GPS, which allows measuring minimum stream widths consistent to less than 1 meter. The RTK base station consists of a high-gain GPS antenna, a power and communication module, and a mounting tripod. Moving vessel the bolts that was executed in the measurements. We have a high-gain antenna, the transducer, and a power communication module also, and a laptop. There are 4 different configuration options to mount the M9 system. A direct connection with the M9, Bluetooth connection, spread spectrum communication, and RTK GPS connection. For this work, the RTK GPS option was used. That consists in the RTK base station collecting satellite points, connect to the transducer and the power and communication there in the boat, connect to the laptop, where the command to start and finish the measures can be controlled, and also analyze the quality of the measurements performed. 2 boats were developed for field measurements. One is a board designed to perform measurements using a rope to conduct the M9 through the defined sections. The other is a manually piloted boat that were 62 pieces printed in the 3D printer and glue with glass design that was built to measure long river sections. Here we have a video of our crew at the São Marcos River that is downstream of the downstream of the hydraulic power plant from CEFAC. Here in orange is our boat, our manual pilot boat, getting ready to perform measurements. I don't know, this black dot here, it's me, operated the drone. And this is the power plant. Now, moving on. Here we have an example of the output from the M9 equipment from the measurement made at the São Marcos River. Here we have the bathymetry and the velocity profile from each section measuring in the site. Now, a brief and summarized explanation on how to measure the energy potential from rivers by knowing the velocities presented. The velocity profile in rivers and channels decay in a form that can be calculated by a logarithmic law or by a power law. These works apply 2 techniques to measure the velocities at water flows. The ADCP calculates a mean values for the column of water through all the cross-section. So to calculate the power density measured by the ADCP, the mean velocity value from it was used. Different case for the LSPAV. They use this power law to calculate the velocity to use in the calculation of the power density. The ULSPAV is calculated by gathering the mean values of the superficial velocity that correspond to 75% of the total length of the cross-section. Both edge velocities were excluded from the analysis due to the possibility to install a hydrokinetic turbine in the margin of channels and rivers that are too shallow. For each cross-section, the diameter of the fictional turbine was calculated based on a simplification that is equal to 2/3 of the maximum depth of each section. There is some important restriction, operational and practical, for installing a hydrokinetic turbines. A basic protocol must be followed to guarantee ideal installation for the Hydrokinetic part. Now we start the section of field measurements and results. The field experiments conducted with the LSPV in the ADCP techniques will be presented with the results obtained from each measurements. Here in this video, it's possible to see the Descoberto Lake at the back. The Descoberto Lake is a primary water reservoir from the Federal District. Its main tributary is the Rodeador River, as we can see here. And in the 70s, it was buried to create the Rodeador Channel. The Rodeador Channel is the largest irrigation channel in Federal District, and this is located in the administrative region of Braslândia. As mentioned, the channel was made by burying the Rodeador River, and through a float gate that is regulated by ADASA, the flow passes to the channel. ADASA is the water agency for Federal District. So we perform measurements in both the Rodeador River and the Rodeador Channel. First, the results from the channel will be presented, and then the results from the river. Here we have the region of interest defined at the Rodeador Channel, and as previously mentioned, 3 sections will be extracted to compare with the ADCP measurements. Here we have the output of the velocity vector field from the LSPV analysis adding sawdust. Here we can clearly see how the addition of sawdust improves the LSPV analysis. Where we have the addition of sawdust in the river flow, the analysis is more uniform and concisely than where in regions that we do not have. We have these crazy vectors. The red masks, as I mentioned, is a location where we do not perform velocity analysis. And after that, we extract in 3 sections the mean velocity from each section. Here's the velocity adding sawdust. And here's the velocity from each section without adding sawdust. Here we have the output from the M9 equipment, the ADCP equipment. In each section, we have the bathymetry and the velocity profile. So using this velocity profile, we plot the mean value from each column of water through all the cross-section in each section. And then we plot the 3 methods together, the ADCP, the LSPV with sawdust, and the LSPV without sawdust. From this graph, we can clearly see how the LSPV with sawdust and the ADCP achieve similar results, and the LSPV without sawdust achieve a good behavior of the velocity, but the values of the velocity was almost double from the other methods in all 3 sections. So after that, we plot the mean velocity from each section, comparing the methods. The blue is the LSPV with sawdust, the orange, the LSPV without sawdust, and the green, the ADCP measurements. Then, using the area measured by the ADCP, we plot the discharge from each section. And finally, we calculate the power density in each section. Just to record you, to calculate the power density, the mean velocity from the LSPV analysis was calculated using the power law. Now we go to the Rodeador River. Here's the region of interest that we define the river. Doing the same procedure, we start recording with the drone, add sawdust, record with sawdust, then we took off the drone, land the drone, insert the ADCP equipment, measurement in all 3 sections, and then we go to the processing phase. Here's the output from the Rodeador River, adding sawdust. As you will be able to see in this video, it's different to see the sawdust in this river because there was a lot of turbulence in this river section because there are a lot of rocks here. So because of that, you're going to see that the results from the LSPV method with sawdust and without sawdust was pretty much the same. So here we have the mean velocity from each section from the Rodeador River with sawdust. Here's the output of the LSPV analysis without sawdust. And you're going to realize it seems like the same video, but it's different. Just to point it out, the mask defined this in this video, it was really good. It was really established in the same place. As you can see in this rock that was in the middle of the region of interest. It did not change the position for all the video. So it shows how good was the analysis made. And here we have the mean velocity from each section, now without adding sawdust. And finally, the results from the ADCP equipment. Even though it was possible to measure the select site with the M9, the location area did not follow the recommendation for a good place to perform the analysis. The water level was too shallow, and the riverbed had a lot of rocks. As you can see in these results from the ADCP, we didn't collect velocity information from all the cross-section. Here we plot the mean velocity from each section. And doing the same procedure, we plot all results together. We can clearly see how the LSPV with and without sawdust achieve some similar results. This happened because the turbulence caused a natural foam that worked as a natural trace in the river. That made the addition of sawdust to not cause a huge positive impact in the analysis. Now, all the mean velocity from each section are plotted together, following the same procedures from the channel. Then, using the area measured by the ADCP, we calculate the discharge. And finally, the power density from each section. Okay, here's the last field site that is located downstream from the Serra do Facão hydroelectric power plant, the São Marcos River. Here I have a small video from the field location, so you can situate where were it. The power plant had an installed capacity of 212 megawatts. That's enough to supply the energy demand of a city with 1.2 million inhabitants. Also, for this field experiment, it was not possible to add sawdust. However, we had the measurements made from the hydroelectric itself of the discharge that was going out of the power plant. So we have a good and accurate value to compare with the ADCP measurements and the LSPV technique. The sequence of data assemblage followed the same from the other field experiments. Mount the ADCP equipment, then define a region of interest, then perform measurements with the ADCP equipment after the drone has recorded the flow. So here we have our region of interest, define the São Marcos River. Following the same procedure, define 3 sections to compare the ADCP measurements with the LSPV analysis. Here we have the output of the LSPV analysis from the São Marcos River. In the boat, our crew waiting to perform the ADCP measurements. So moving on, here is the results from each section, the mean velocity plot without sawdust. As I mentioned, it was not possible to add sawdust to these field experiments. Now we have the bathymetry and the velocity profile from each section from the São Marcos River, and the mean velocity from each part represented by these red dots, plotting all together in each section. Section 1, then section 2, and finally section 3. And we plot the mean velocity from each section, comparing the methods, the LSPV without sawdust and the ADCP technique. Using the area measured by the ADCP, we calculate the discharge. Important to mention that here we have the value informed by the power plant, is the blue here, this effect measurements. In the day that we performed the measurements, they were recording 89 meters per second discharge. And it's really close to the values recorded by the ADCP, just proving how accurate and reliable the ADCP equipment is. And finally, we calculate the power density from each section, comparing each method. Now, to conclude this section, I bring a summary of the velocity measured from each method and in each field. Just to point it out, I want to remember that the LSPAV measures the superficial velocity, different from the ADCP that measures the mean velocity in the column of water. Applying the power law, the velocity from the LSPAV and the ADCP, in some cases, like the one from the rodeador channel, with the addition of sawdust, achieve some similar results. I would like to comment how impressive is the drone to field work. Besides doing all the LSPAV recorded, it was also made an orthomosaic photo and a digital superficial model from the power plant. It's just to illustrate how powerful this equipment is. Finally, my conclusions are: Hydrokinetic energy can provide a renewable energy source for isolated communities in Brazil. LSPAV proves itself a reliable, safe, and simple methodology to characterize the superficial velocity from rivers and channels. The approach to correlate the technique LSPAV to hydrokinetic potential is audacious, but the results proves that it's possible to use in an initial field investigation to analyze possible areas to implement an enterprise involving kinetic energy. Further experiments and analysis must be done to assure that the LSPAV can determine the hydrokinetic potential. Combining the LSPAV with the ADCP is an efficient and accurate methodology to determine the potential. Adding a natural tracer improves the results of the LSPAV method when the river does not have a notable trace of its own. It's important to recreate the field environment in a laboratory, so a more controlled and precise analysis could be performed. This work achieves its main and secondary objectives. It's expected that these works also serve as a manual to field measurements applying the LSPAV methodology. Thank you very much for your patience and time. I hope that I managed to explain my work in a succinct way in this presentation, and now I'm able to clear any doubts about the work. Once again, thank you, merci, e obrigado.
Thank you, Felipe, for your presentation. And I'd like to, firstly, I'd like to talk that this work was performed in the framework of one of our R&D projects with the Serra do Facão company. Is a electricity company that works together with us in the context of hydrokinetic potential, reminiscent flow of hydropower plants. Is a research area here in the Laboratory of Energy and Environment of University of Brasilia. And I think most of founding of this experiment was performed with this collaborating project with this partner. So I'd like to have some consideration of the jury. I will start with the consideration of Pierre MARUZEWSKY, a great friend of mine. It's a very pleasure to have you here online in the first moment, but I think you will be among us on next year, I think, in Brasilia to join us another time. So up to you, Pierre, for your comments.
So thank you, Antonio. Sure, I will be happy to come back in Brazil as soon as was possible, but it will be perhaps next year or in 10 years, we don't know. So Felipe, obrigado for this amazing work, experimental work. When I read and now see how you mixed well equipment, new equipment, software, and all of that analysis. I have few remarks and comments and questions about both techniques, or three techniques: LSPIV and M9, and LSPIV and ADV flow tracker. You don't talk today about ADV flow tracker. And first, when you consider with and without sawdust, I understand when there is a natural sawdust, we can say that the turbulence is a natural sawdust, okay? And when you showed the result, that there was no difference with and without sawdust due to the turbulence. So for all rivers where you will find turbulence, you don't need sawdust because you have already did it, and you have the same results. Now about the radiator channels, okay? So you see how it was important when you have a quiet river to add sawdust, okay? To see the velocity field and the flow. But in your report, you compare both techniques, LSPIV and ADCP, and LSPIV and ADV. So how can you explain that in the same channel, in some radiator channel, you have first difference between cases with sawdust and without sawdust for LSPIV and M9, and you have no difference when you use LSPIV and AD flow tracker in the same condition, in the same channel river, that it is a quiet river.
Okay, thank you, Pierre, for your questions and your comments about my work. The measurements made by the ADV equipment, the flow track, was an invitation from ADASA to perform measurements, and it was not made in the same day that we perform measurements with the ADCP equipment. So it was different, and the discharge that passed through the channel changed from seasonal here in Brasilia. So when we got to the raining station here, they open a little bit more the flow gate to pass more flow. So the results from both measures supposed to be different. And but you were asking why the ADV and the ADCP, in the ADV, the measurements with the sawdust in the without sawdust didn't change a lot, but with the ADCP changed a lot. Because the location that we performed the measurements was also different from the Rodolfo channel. The measurements that we made with the ADV equipment was right after the flood gate. So it also had a little bit of natural turbulence of it because it go under the float gate and it caused a little bit of foam already. The position that we performed the measurements with the ADCP, it was like 15 meters upstream from that region. So maybe that's why it caused difference in the results.
So I think you can add a few sentences about that in the section when you explain and present results for LSPIV and ADV flow tracker, because first we have difference, no difference, and at the end on the river we have no difference because due to the turbulence with and without. So for me it's clear it's the same things. Okay. Now if we go to São Marcos River, just a moment. Wait. When you compare LSP LSP methods and ADCP methods, okay, and when you draw the velocity profiles, we saw that there are the behavior is different from LSPIV and from ADCP. So that means the velocity field is different and the value of the velocity is different. And at the end, when you compare the discharge calculated from your measurement with ADCP and you compare to the real discharge from the hydropower plant, you found the same. So how can you explain? Because the velocity from ADCP is not the good velocity, the real velocity. And the discharge, if you calculate the discharge, you calculate discharge from the velocity. So I don't understand how you can catch the same discharge at the end between the power plant and your results.
The ADCP measures the mean velocity from each section, and it also measures the discharge from each section. So
so the discharge is not a calculation; it is a measurement. You take a measure of the discharge with
yes,
your equipment.
Yes, but if the output of the equipment, it showed me the discharge, but if I took the velocity mean from the channel and multiply by the area that he also calculates, it gives the same discharge.
Okay, so if you have the discharge and you can calculate it by the post-treatment of your drone, like the area, okay, you can calculate the velocity and to see if it's the same or not, because you take you plot the velocity from the measurement, you plot the discharge from the measurement, but you can compare now if you calculate the velocity from the discharge measurement, because you have the area on your rest of interest, you can find the velocity and compare with your measurement.
Yes.
No, it's an open question, not just for you, but for Antonio and.
I think, Pierre, you're right. I think the large LSPV is not a good method to estimate the whole discharge, because you have to take some kind of consideration to be in the profiling up to the bottom of the river. So at this moment, for simple channels, like for example, roteador channel, it's very easy to determine the some kind of parameterization to use the surface velocity by measured by the LSPV and to go up to the bottom of the river. But for example, in a complex river, it's very difficult to do that.
Sure.
Yes.
It's just working for the channel, for the rodeor channel, because everything is quiet and you have everything.
Yeah.
But,
yes.
And when so, in my point of view, Felipe, it's very easier to have a good
measurement in the rodeador channel
to estimate the hydrokinetic potential, because we have the velocity vectors and we can have some specific areas to, for example, to installate a turbine. But when we integrate, I don't know. I have many errors here. For example, in roteador channel is a trapezoidal cross section, so it's easier to do that. I think the answer is that. I don't know. It's an open question for me, because the field campaign is very difficult, and Felipe had pointed out that it's easier to control the experiment in some kind of laboratory experiment, smaller, and calibrate the models exactly to reproduce the more complex rivers to have the integrated values. I think it's that, Pierre. I don't know.
Okay. I agree. It's it will be a next analysis or next work. So I have no more technical questions. I think for next week I will send you all my comments about typography and English in your reports. Okay, but congratulations, it's a good work, good jobs.
Thank you very much.
Thank you very much, Pierre. And it's a very good discussion, because when we are in field, it's very and I think it's a good methodology now, and that we have used it. But for example, in my point of view, you can use it, for example, for large rivers, for example. I don't know. It's not possible, and I think mainly considering the sun dust necessity to improve the results with some kind of war, some kind of turbulence in the waters, to have specifically the marker particles to perform the PIV computation. I think but it's a good methodology to have some kind of real results, rivers, to choose a good site to install a hydrokinetic system device. Thank you another time, my colleague, and we hope that you will see soon in on some days, I think. And so another consideration, Felipe, to Pierre.
No, for me, I appreciate a lot he being here today. Thank you for your suggestion and comments. It's, as Professor Brasil told, it's a experimental technique, and definitely it's, like I said, it's audacious to say that we can determine the hydrokinetic potential of the LSPV technique, and we definitely need to bring this analysis to the laboratory so we have a more precise and controlled environment, so we can definitely see how it works, the superficial velocity to the decay of the velocity profile in each section. It's a really good question, and I agree with you. In a small trapezoidal channel, it's really easy to measure, but when we go to big rivers with long streams, it's hard. I still want to go back there and do the experiment with sawdust just to see if get anything better. But maybe in the next few weeks, with Rafael that is watching us, we can go there and perform all the measurements. But thank you very much, Pierre. It's a really honor to have you here.
Yeah, thank you.
I would like to pass to Taygoara considerations. So up to you, Taygoara.
Thank you, Brasil. Thank you, Felipe. Nice to meet you, Pierre. Thanks a lot for your comments, and thank you, Felipe, for your presentation, for your work in our lab. I enjoy your presentation, and I have read your report too, and I have several comments, and I think pretty much like Pierre, I did some small, medium, and big observations in your report, and I will pass it to you after this exam, and maybe you can improve the report and the English and maybe the analysis too. I will pass. I'm going through my comments right here and to see if I found something important to say. Well, in a very general sense, I think I will give you one or two words on your report. In a very general sense, I think you must to take care of your figures, of your captions, and the quality of the work, of the pictures. You know, some are very simple pictures, kind of lazy, and there is no reason to put some bad pictures in your report. Pretty much like figure 1.1 is a simple plot that you can do better, I am sure. Even figure 1.5, it's hard to understand unless you have some knowledge on the field. Maybe you can put real turbines, and I don't know. If you check your report, you're gonna understand what I'm saying. Well, my most important point I think, was partially covered by Brasil and Pierre. So I have several questions. When you put your methodology on the paper, I don't think you did a very good job. You focus on describing each technique. You describe the ADCP, you describe the camera and the camera system, the PIV system, and your processing methods. But the way you perform your runs must be better, must be improved, and you must describe it better. I mean, when I read your report, I would expect somewhere you explain how the essays were done. You know?
How the what, Professor?
The essays, the runs, the experimental runs, yeah. Right? Because several doubts came to me after reading your text. I will read some of them. Okay, where the AD, I think you should provide a proper methodology description. So some questions that are hard to respond, to answer, just reading your book, your dissertation. Question 1, were ADCP and movie recordings done at the same time? How do you assure that with and without tracer measurements are made in similar condition to make fair comparisons? Because it's simply loose, you know. You put the tracer and you just wait a little bit and made another measurements. Were the flow conditions the same? I think you have a good idea on that, but it's hard to the reader to buy your points, or to believe that you are measuring the same thing with the both methodologies. One question that's hard to answer to me: what's the role of the height of your drone flying? If the drone is too high, can it distinguish the particles? In fact, I would like you to talk a little bit on that. Do you really think that your drone, your camera system, your PIV system, the large scale PIV system, are really seeing the particles, the tracer particles?
Professor, there are studies that are using satellite images to perform LSPAV analysis. I truly believe that the method that I choose, we perform our discrete Fourier transformation. So it's not analyze the image domain, but it's analyze the frequency of the color of that pixel. So yes, I have to believe, and I do believe, that in the interrogation area that I define, it's characterized one pixel of it, and is looking for the same pixel with the same frequency in the frame right after the frame.
I think you reach a point very important that I pointed out too. How can your system decide if he is seeing sawdust or light in the surface, scattering? Because your pictures, depending on the conditions, we are seeing a lot of light in the surface, and turbulence induce light scattering in the surface. So are you recording sawdust, or are you recording light scattering?
Well, I can be recording both simultaneously, but the method has an error. But the idea is like to, of course, you have an error, but the idea is not to analyze just one pixel to the another, but a conjunction of pixels.
I understand the idea of the method. You do statistical correlations to understand if a bunch of particles are moving together in some velocity. So At the end of the day, my point is that one. I really think that you catch a methodology and use it in an open field without controlling the environmental variables. So it's very hard to understand if your results are meaningful, if your comparisons are significant. There is a lot of loose points. One, you have cited that at the end of your presentation. AGCP doesn't measure the surface velocity. It measures something else. And your hope is to measure the surface velocity using your large-scale PIV. That's one bad point. So another one is the velocity on the field, on the current you are measuring is pretty much random because it's a natural river. Okay, you have no control on that. So maybe a good idea, not for you, but for your colleagues, the ones that will continue your work. Maybe a good idea would be start in a lab. Maybe in civil engineering lab, where we have pretty much long artificial channel, and to put your drone in a position controlling the illumination, and then you put sawdust and you go clean and you try other particles, and maybe you can try to inject sawdust or tracers in different depths, you know. Maybe we can try something like that. And then controlling the conditions, test if the high of your recording is important. So in that sense, you're gonna get a standard for your LSPIV, because I don't think that your LSPIV have too much correlation with global satellite PIV. I think the idea is completely different, okay, and the method. Then you can move to a small river, because you are leaving part of the control. In the lab, you have total control on the environmental conditions. Then you move to a small river, and then you go to a big river. Okay, so I think this is a very broad sense of my analysis on your results. I think you did a good job, and mainly thinking on the project, because you provide information for the research project. You are working, you are the team, you are a component. So, but in some way, I think that your master dissertation could be focused in just one set of measurements and more analysis on the results you got. One word on your presentation. Every time you have a result, every time, sometimes, most of times, when you project a result, you just put, so this is with sawdust, this is without sawdust, and skip to the other slide. And I would see more analysis on the results and more comparisons and more speculation even. I don't, it's not a problem, okay? But in that sense, I think you should go deeper in analyzing and comparing results in the more critical way in your text and your next presentation, because I'd like to think or to believe that this will not the last one, that you continue working and doing, I don't know, PhD and maybe going further. But you should always focus on getting results that provide good basis for a thesis, for a point, a scientific point, and then you stand on this point using your results and not just showing several results one after one and leaving to me the conclusions, or to your audience the conclusions, right?
Right.
But as you see, I have no questions actually, unless I think you have done a good job, and most important, this is the first job in our lab on large-scale PIV, and this pioneering work is always welcome and harder than the next one. So in that sense, congratulations, and I think you have done a mastership job. Okay.
Thank you, Professor.
So Brasil, I'm satisfied with Felipe's work, and I have no questions and no more comments. Actually, I have several comments on the text, but I will send it for you and for Felipe, and you both together will decide if or what of those, which of those points are deserve to be implemented. All right. So thank you very much. Thank you for the invitation, and thank you, Felipe and Brasil. And I give you the word back.
Thank you, Taygoara. And okay, you are right, and I think Felipe is very conscious that it's very difficult to control all of the parameters for large-scale PIV in the field campaigns. One of my questions is very natural. That, for example, the tracer, the particles of a real turbulent flows, is very difficult to control, because you can have some kind of particle that will naturally destroyed by the turbulence. For example, some kind of small waves, and I can destroy it easily only for the turbulence in the surface of the river. It's a marker that will not be presented in the next image frame. So it's very difficult to use clearly and properly image correlation, consider that the phenomenon of the marker is always a phenomenon related to the fluid flow itself. So, of course,
I think that I understand your point. When you put some traces, the turbulence will, in some sense, to destroy the correlations, and your system will not see anything.
Yes.
I have a last point. Maybe for turbulence or in intense turbulence conditions, or I don't know, you are using a pretty much an Eulerian PIV because you are doing correlations. But it's a possibility to change it to Lagrangian, not PIV. So using large tracers, maybe a buoy, something like that, or several small buoys that your camera is able to see, and then you track and measure the velocity in some Lagrangian way. And maybe this will survive to the turbulence and will provide sharp images that can be analyzed in a more meaningful way, even in turbulent conditions. We'll see the same system, maybe the same system can be used in an Eulerian fashion, like PIV, or in a Lagrangian fashion, like LSV, something like that.
Yes. For example, Felipe had performed some kind of literature review that, of course, there is many rivers that have some kind of some in surface, so it's easier to identify as a particle, not as a turbulence, as a wave turbulence, in my point of view. And I think there is another kind of turbulence. For example, for the second, for Roteador River, not for the Roteador Channel, it's not a deep channel. So at this moment, all of the sand, the turbulence will enhance the sediments in the river that can be used as a marker. But for example, in the Great River as São Marco River, the most of the particle is not a real particle. It's some kind of wave turbulence in the surface of the river. So it will be destroyed not only by the Lagrangian or the streamlines in the surface, but it will be destroyed only for the changing the wave, the surface height in some position. So I really don't know, because at this moment we have to use some kind of marker particles as a some kind of floating materials. I don't know exactly, but I think with at this moment to capture only the tracer, we have to use some kind of altitude to have to identify the particle. For example, zooming with the altitude of the drone. So, but it will be a work in progress. In my point of view, in a practical point of view, not in the hydrological or in the hydraulic point of view, only to identify the greater velocities in a river, to put, for example, the cross section or the transect observation using the second experimental results from the ADCP measure, that is harder to be performed than the LSPV measurement. I think in this point of view, combining the two methodologies, I think it will be the better thing that we will have to do.
I think I got it. You mean we can use the LSPIV to make some preliminary measurements over a large part of the river, and then decide where to make some ADCP measurements.
I think to perform a good potential, hydrokinetic potential for a river, we have to use different methodology, field methodology, like ADCP measurement, LSPV measurement, local point with the floating sensors, and so on. And is that we have done in our Lambari project with the Serra do Facão. So do you think about it? Then I will pass to Felipe to conclude this kind of consideration that we have discussed here. What do you think about it, Felipe, to close the section?
As I mentioned in my conclusions, I said that the LSPV can be used as an initial field investigation, because I was in the field and I know how difficult it's to get to good location measures, because sometimes you don't have the access to the river or to the location that you want to perform. So the LSPV, it's safe, fast, and easy, if you know how to pilot a drone, way to make an initial field investigation. I agree with Professor Taygoara that a lot of work need to be done to know the different conditions, like the altitude of the drone, how important the tracer impacts in the analysis, how much the turbulence can impact, how much are you really seeing the particle or just illumination from the sun in the particle. But to use as an initial field investigation, to say, okay, here we have a good point in this river. Let's now go with the transect, get a crew. Let's go with different field measurements that are intrusive equipments, like the ADCP or other equipments. I think for now, having the results that I have, that I agree they're not really good, it's a good procedure. It's a good methodology. Perform an initial investigation with the LSPV, determine areas that are good, that have a good potential to perform hydrokinetic enterprise with hydrokinetic turbines, and then go with accurate and reliable equipment like the ADCP that we have in our laboratory.
Good, Felipe. One last position here is very important. In another point of view, of course, we are looking to place some turbine in the upstream channel, in the upstream river position from a hydroelectric power plant. Right? On another point of view, there is many important information that have to be used in the discharge and the flow field near to the outflow of the turbines. It's very important as a maintenance and other thing related to the channel, just at the exit of the flow exit of the turbines. It's very important, for example, our patterns, and it's very easy because in this region, in the outflow, the channel is very regular. Okay, you have a channel that had built in the hydropower plants. So at this moment, the LSPV for the first region in the outflow is very interesting. In this case, specifically in the case of the Serra do Facão hydroelectric power plant, there is another important feature in the flow field, in downstream flow field, because we have a discharge, a bottom discharge in this dam. And so the flow is very interesting. We did not investigate this flow exactly in the outflow reservoir, but it's very interesting to investigate for, of course, to characterize the flow, not for the hydrokinetic turbine, but the outflow characteristic in the hydropower plant.
I think, Antonio, it's a good point, because in the Taylor channel, you have only kinetic energy and small velocity, and the flow is very quiet. So it would be a good test case where to do it.
Yeah. Okay. Thank you very much for all, and I will open to the audience. If you have some questions or some consideration, so we are open for you. Please, some consideration, everybody.
Tudo bom.
So, Taygoara, how we have to do that? We stay in this same.
No, I think you can. Maybe I can set another meeting, and then we flip to that. And Felipe, stay here, waiting for you and probably me and Pierre. Okay.
Will you open another section?
Yes, I will open another section, and I will invite you and Pierre. Oh,
okay.
I hope I can invite Pierre. Let me see. Give me 1 second, please. I have a, that's gonna be fast. Maybe I can set up a Google meeting. It's easy, huh?
I don't know. Here I had the option to break out rooms. Okay. Yeah.
Google Meeting is not possible for me because I'm at EDF offices and it's forbidden. So.
Oh. So Felipe, help me. What are you saying?
I can try to create this breakdown room, put all of you together, then I go out, you discuss and talk about my work, then you come back.
And then we go back. So
okay.
Yes.
Okay, stop the recording, please.
Oh yeah.
Oh. I can do that. Maybe you, Felipe.
Yeah.
Rafael, you can use it, this presentation of Felipe for our report for Serra do Facão next month, please.
Okay, I will move now Professor Brasil, Dr. Pierre, and Professor Taygoara to the other room. I don't know what's going to happen because I never did that. I hope I do the right.
We'll see.
No, I don't understand, please. Eu deixo aberto isso aqui?
Yes.
Okay.
It transfers like in Cosmos 99, you know, you can go.